The universe is a strange and wonderful place, especially when you dive into the realm of the very small. This is the quantum world where the familiar rules of classical physics break down and things get really weird. Here, particles can be in multiple places at once, and cats can be both dead and alive. Welcome to the mind-bending world of quantum mechanics. This isn't just some abstract theory, it's the foundation of our understanding of atoms, light, and the very fabric of reality. Quantum mechanics has led to incredible technological advancements, from lasers and transistors to the promise of quantum computers, and at its heart lies one of the most bizarre and intriguing concepts of all: superposition. Hold on tight as we embark on a journey into the heart of quantum mechanics. We'll explore the mind-bending concept of superposition, where particles dance between multiple states, and reality itself seems to shimmer with uncertainty. Get ready to have your mind blown. In our everyday world, we're used to things behaving in predictable ways. A ball thrown in the air follows a parabolic arc and a dropped object falls to the ground. This is the realm of classical physics, governed by Isaac Newton's laws of motion. But venture into the microscopic world of atoms and subatomic particles, and these rules no longer apply. Quantum mechanics, developed in the early 20th century, is a set of principles that govern the behavior of matter and energy at the atomic and subatomic levels. It's a radical departure from classical physics, challenging our intuitions about how the universe works. One of the key differences is that in the quantum world, things aren't so clear-cut. Instead of definite positions and velocities, particles in the quantum realm are described by probabilities. They exist in a haze of uncertainty, their properties smeared out like a blurry photograph. This is where the concept of superposition comes into play. Imagine a coin spinning in the air. It's neither heads nor tails, but in a state of both possibilities simultaneously. That's the essence of superposition. In the quantum world, particles can exist in multiple states at the same time, defying our everyday experience. Think of an electron, that tiny negatively charged particle that whizzes around an atom's nucleus. According to quantum mechanics, an electron doesn't follow a well-defined path like a planet orbiting the sun. Instead, it exists in a superposition of states, meaning it's in multiple places at once. It's like being able to be in New York and Los Angeles simultaneously. It's only when we make a measurement, trying to pin down the electron's location, that this superposition collapses, and the electron chooses a single state. This ability to be in multiple states at once is what makes superposition so mind-boggling and so powerful. Section 4: Schrödinger's Cat, Dead and Alive. To illustrate the strangeness of superposition, Erwin Schrödinger, one of the pioneers of quantum mechanics, devised a thought experiment in 1935. Schrödinger was a brilliant physicist who contributed significantly to the field of quantum mechanics, and his thought experiment remains one of the most famous and perplexing illustrations of quantum theory. It involves a cat, a box, and a lethal dose of poison. The setup is simple yet profound, designed to challenge our understanding of reality at the quantum level. Don't worry, no actual cats were harmed in the making of this experiment. Schrödinger's cat is purely a theoretical construct, meant to provoke thought and discussion. Imagine a cat placed inside a sealed box. This box is completely isolated from the outside world, ensuring that no information about the cat's state can escape. Also inside the box is a device that has a 50% chance of releasing a deadly poison within an hour. This device is connected to a quantum event, such as the decay of a radioactive atom, which is inherently unpredictable. Now, according to quantum mechanics, until we open the box and observe the cat, it exists in a superposition of states. This means that the cat is simultaneously alive and dead, a concept that defies our everyday experiences. It's both alive and dead at the same time. This duality is a fundamental aspect of quantum mechanics, where particles can exist in multiple states until measured. This thought experiment highlights the counterintuitive nature of superposition. It forces us to confront the bizarre implications of quantum theory, where the act of observation plays a crucial role in determining reality. Our intuition tells us the cat must be either alive or dead, even if we don't know for sure until we look. This intuitive understanding is rooted in classical physics, where objects have definite states. But in the quantum world, things aren't so black and white. Particles can exist in multiple states, and their properties are not determined until they are observed. The cat's fate remains uncertain, suspended in a limbo of possibilities until we make a measurement. This uncertainty is a hallmark of quantum mechanics, challenging our perceptions and inviting us to explore the mysteries of the quantum realm further. Schrödinger's cat continues to be a powerful metaphor for the strange and fascinating world of quantum physics, where reality is not always what it seems. Section 5. The wave function, riding the probability wave. How do physicists describe a particle in superposition? This is one of the most intriguing questions in quantum mechanics. They use a mathematical function called the wave function. This function is central to the theory of quantum mechanics. Don't let the math scare you, it's not as complicated as it sounds. The wave function, often denoted by the Greek letter psi, is a tool that helps us understand the behavior of particles at the quantum level. The wave function is like a map that tells us the probability of finding a particle in a particular state when we make a measurement. Just as a map shows different locations and landmarks, the wave function provides a landscape of probabilities. Think of it like this. Imagine a wave spreading out on the surface of a pond. When you throw a pebble into the water, it creates ripples that move outward. The height of the wave at a particular point represents the probability of finding the particle at that location. Higher waves indicate higher probabilities, while lower waves indicate lower probabilities. The higher the wave, the greater the likelihood of finding the particle there. This concept is crucial for understanding phenomena at the quantum level. The wave function doesn't tell us exactly where the particle is, but rather gives us a range of possibilities. It's like having a weather forecast that predicts the chance of rain in different areas. It's like saying there's a 60% chance the particle is in this region, and a 40% chance it's in that region. This probabilistic approach is what makes quantum mechanics so different from classical physics. This probabilistic nature of quantum mechanics is one of its defining features. It challenges our classical intuition and forces us to think in new ways about the nature of reality. Quantum mechanics has profound implications for technology, leading to advancements like quantum computing. These computers use the principles of superposition and entanglement to perform calculations far beyond the capabilities of classical computers. As we continue to explore and understand the wave function, we unlock new possibilities for innovation and discovery. The future of technology and science is deeply intertwined with our understanding of quantum mechanics. Educating the next generation about these concepts is essential. By demystifying the wave function and making it accessible, we inspire future scientists and innovators. Collaboration and communication are key in this field. By working together, scientists can push the boundaries of what we know and explore the uncharted territories of quantum mechanics. The wave function is not just a mathematical tool, it's a gateway to understanding the universe at its most fundamental level. It invites us to ride the probability wave and explore the mysteries of the quantum world. Section 6. Measurement. Collapsing the wave function. So, what happens when we make a measurement and try to pin down a particle's state? In the quantum world, particles exist in a state of superposition, meaning they can be in multiple states at once. This is a fundamental concept that defies our everyday experiences. This is where the wave function comes into play. The wave function is a mathematical description of the quantum state of a system. It encapsulates all the possible states a particle can be in, represented as a wave of probabilities. When we make a measurement, we're forcing the particle to choose one state out of the many possibilities it was in superposition. This active measurement is not just a passive observation, it actively influences the state of the particle. This active measurement is what's known as the collapse of the wave function. Before the measurement, the particle exists in a cloud of probabilities. But the moment we measure it, the wave function collapses, and the particle snaps into a definite state. It's like the wave on the pond suddenly disappearing, leaving behind only a single ripple at the point where we made our observation. This analogy helps us visualize the abstract concept of wave function collapse. The particle is no longer in a blurry haze of probabilities, but has snapped into a definite state. This definite state is what we observe and measure, giving us concrete data to work with. The collapse of the wave function is one of the most debated aspects of quantum mechanics. It raises profound questions about the nature of reality and the role of the observer in the quantum world. Some physicists believe it's a real physical process, a fundamental aspect of how the universe operates at the quantum level. They argue that the act of measurement causes a real physical change in the state of the particle, while others see it as a mathematical artifact of how we describe the quantum world. According to this view, the wave function collapse is not a physical event but a change in our knowledge about the system. Regardless of the interpretation, the act of measurement plays a crucial role in how we understand and interact with the quantum realm. It bridges the gap between the abstract mathematical descriptions and the tangible reality we can observe and measure. The debate over the nature of wave function collapse continues to inspire new research and experiments. As we develop more advanced technologies and experimental techniques, we may one day uncover deeper insights into this mysterious process. For now, the collapse of the wave function remains a cornerstone of quantum mechanics, a reminder of the strange and fascinating nature of the quantum world. It challenges our understanding and pushes the boundaries of what we know about the universe. As we continue to explore the quantum realm, the mysteries of wave function collapse will undoubtedly remain a central topic of inquiry, driving us to question, explore, and ultimately understand the very fabric of reality.